Hello and welcome to my presentation. I am Darren D'Souza, conveying my work on safe and energy-efficient motion planning, a human-robot collaborative scenario. This work was carried out at the Robotics Innovations Lab, Indian Institute of Science, Bangalore. The presentation consists of the following sections. Human-robot collaboration has been developing at a rapid rate, but a paramount challenge to it is the integration of human coworker safety while maintaining the performance objectives. The objective of our work is to introduce a safe motion planning framework for human-robot collaboration in industrially constrained settings where path replanning is infeasible. We also develop a performance evaluation metric to evaluate our system's performance. The motivation behind this remains the development of human-robot trust of interaction using safe and energy-efficient processes. In comparison to the prior art, our work contributes to an adaptable task space mapping, safe and energy-efficient path planning, and the development of an evaluation metric to increase human-robot trust of interaction. Our proposed approach for safe and energy-efficient motion planning is a combination of an energy field-based planner at a global perspective, multimodal communication for human coworker ease and safety, as well as optimal path planning alongside safety evaluation using constant human motion tracking at every point in the control cycle. In our gesture-based communication module, we combine YOLO V7 and media pipe-based skeletal detection to identify gestures as task inputs. Let's see it in action. Our dynamic task space mapping helps human operators guide and teach the robot about its environment, in turn reducing search space complexities. The generation of energy fields helps guide the robot's end effector towards the goal while it repels obstacles along its path. Here is a gist of the mathematical formulation. Multi-objective optimization has been performed using the gradient descent algorithm, taking the path length and bending energy of the path as parameters, hence choosing the best path for the given scenario. The safety evaluation module is the core block defining the safety based on predefined zones and constant human motion tracking with respect to the point of interest between human and the robot's end effector, while the performance recovery module helps the robot regain maximum speed when it is labeled safe by the safety evaluation module. Our simulations have been carried out on ROS Noetic using the Gazebo physics engine. We perform an algorithmic study for various test case scenarios to determine the best fit algorithm for our application. The results of our simulation highlight the dominance of the improved artificial potential field algorithm across various test cases and hence proves to be the best fit for our case study. Our experimentation has been performed using a UR5 robotic manipulator in a constrained industrial environment like setup. The study simulates an electronic waste sorting scenario, assigning the robot the task of sorting motors and batteries into designated bins. The experiment begins with the human operator in the green zone. Based on the human's approach towards the robot, trajectory scaling occurs. A thorough study of position and velocity profiles of the human's closest point in the robot's reference frame has been studied, and notable deviations in velocity for various zones were observed based on the safety evaluation module developed. In advancing human-robot interaction systems, we introduce a unified performance metric seamlessly combining safety and efficiency. This innovative metric offers a clear, trustworthiness score enabling reliable interactions. In conclusion, this work presents a kinematic strategy for safe and energy-efficient motion planning. Our approach leverages multimodal communication, simultaneously demonstrating effectiveness through optimal path planning backed up by simulations and experimental validation. Our system achieved 83.87% effectiveness score relative to an ideal case scenario. This affirms concurrent reliability in safety and efficiency and the system's nuanced capabilities, which emphasize the need for ongoing refinement for heightened trustworthiness. Our future work aims at refining safe motion planning with predictive control mechanism for smoother speed profiles, as well as the establishment of a standardized universal safety metric for human-robot collaborative scenarios. Thank you for listening.